Okay, we are going to learn about accumulation function. So this is page number 32 in your packet. This is again page number 32 in your packet. So let's take a look at this. We'll be doing this homework in class, so don't worry about the homework, but in case if you want to see what we are going to do, so page number 35 and 40, you can continue. Check it out at home if you want to. So let's take a look at it. Now we understand the concept of the finite integral is nothing but the area. So let's consider a special type of function. Suppose we have f of x equal to 2, which is nothing but the horizontal line here, f of x equal to 2. Realize that the equation f of x2 is the same as f of t is equal to 2, f of k is equal to 2. It's just that variable is different. That's all. So we are going to use a different variable t here. There is a reason for that. We are going to use a t. So consider this expression. Consider this expression 0 to x f of t dt. This is a function of x which represent area under the curve f of t starting from t equal to 0 ending at t equal to x. So as x changes, area is also changes. So think about, let's complete this chart. If I say 0 to 0, substitute 0, 0 to 0, area is 0. If I substitute 1, so that means what's the area from 0 to 1? You can count the block area from 0 to 1. We have 2 blocks. As we continue, so you might want to pause the video here and fill in this chart, or you can just continue. Just fill in this number 0, 8, 10. So we can see that it's apparent that x get larger and larger, the area increases as well. So this is called accumulation function. We give a name. This is called accumulation function, which collects the area starting from 0 to x, and we call accumulation function. So if I say this, let me adjust my frame here. It's slightly not clear. Changing this one, not the other one. Okay, so I'm going to bring my answers here. So 0 to x f of x dx would be confusing. So know that you will never see the reason. Now you realize that why we use the letter t. It's so much easier to see that area under the curve, the x is just the variable that x changes. So to the right, the function is f of x equal to 2x. Let's take a look at this. Another function f of x is 2x. And if I find the area 0 to x, keep changing, 0 to 1 is 1, 0 to 2, area of this is 4, 2. Check the scale. This is confusing because the scale is going by 2, 4, 6, 8. Look at the scale. The x and y axis has a different scale. Let me erase that. X and y axis has a different scale. So if I go from 0 to 0, then area 1/2 base times height. So that's a 1. If I look at this 2, so I have 2 blocks, but the scale is double. So if I go by 3, 1, 2, 3, 4 and half, scale is, so that's a 9. And that number is 16 if I count the area. Carefully check the vertical scale is by 2. So now we plot these values on the same graph and connect them with a smooth curve. The curve should be familiar what this is. So this is a line and I'm going to plot this area. So 0 is a 0, 1 is 1, 2 is 4, 3 is 9 and 4 is 16. And we can see this graph, what's this, looks familiar. This looks familiar. We should be able to make connection that this is a y equal to x square and this is a 2x. Now everybody should know the relationship between x square and 2x. What's the relationship between x square and 2x? So my when I sketch this graph, I have the equation which is called x square. So now let's take the derivative of this. What do we get? So remember, this was my function x square, and if I take the derivative of this, I get the 2x. This is x square. Take the derivative, I get the 2x. This leads to a very important result. So I believe we have discovered a very important result here is this. Make a box over this, memorize this, know this all the time. So let's talk about what this is. We study this formula in a great detail later in this chapter. Not the later, we are going to do this in class on Monday. But this says the slope of the tangent line to the accumulation of the function is function itself. Okay. If we start with a function, accumulate it, then take its derivative, we end up back with a function, and that is called fundamental theorem of calculus. Simple language. What the simple language is, derivative and antiderivative, you get the original function back. Simple language is derivative of the antiderivative, you get the f of x back. But we don't get f of t, we get f of x. So that's the fundamental theorem of calculus. We are going to learn about this in more detail in class. But let's see how we use of accumulation function and where it is being used. Accumulation function is going to be one of your free response question in AP PC calculus exam or even AP calculus exam. This is going to be a free response question, and let's take a look at the next page, page number 33 in your packet. Okay, so let's start. F of x, uppercase f of x. Don't worry about this name. Let's talk about uppercase f of x is 0 to x f of t dt, where f of x graph is shown to the right. This is f of t dt is shown to the right. Remember, f of x is the same as f of t. To make this easier, understand f of t is the rate of snow accumulation over an 8-hour period. Okay, so this is a rate of snow accumulation. T is equal to 1. The snow is falling at the rate of 3 inches per second. So you can see that the rate in here is inches per second. And think about this unit is a second. T is equal to 3. It is not snowing. 3 rate is 0, so it's not snowing. T equal to 4, snow is melting. You can see that the rate is negative. So snow is melting, negative. And like that. So let's complete this table. I want you to pause the video here for a minute and complete the table. 0 to 0, area is 0. 0 to 1, 0 to 1, you can see those two tiny. So I'm going to fill in this blank. You might want to pause the video and find those area, and then you can check the answer. I have simplified my answers for easier to write. You might want to write that as it is, what you have, something plus something minus something. Remember, we are going this way, so this area will be counted negative. That's the positive area, that's the positive area, that's the negative area. Okay, so let's see what we have next is we found this area. Now we have seen that derivative of the accumulation, you get the original function back. So if I write this inside as f of x, and if I take the derivative on both sides, watch that, this I take the derivative on both sides. This is very important to understand. If I take the derivative of f, it becomes f prime. if I take the derivative of antiderivative, I get f of x. So if we keep this in mind, that the derivative of antiderivative, we get the original one back, how do we complete this table? How do we complete this table? So now I'm going to complete this table in terms of f of x, which is simply the y value from the graph. This is nothing but the y value from the graph. This is nothing but the y value from the graph, which is also f prime of x. So I'm going to bring my answers here. Okay, so these are nothing but the y values from the graph itself, y values from the graph. Okay, so now we are going to go back into our previous unit where we have to discuss where f of x is increasing, decreasing, and which is very similar. You all have done a great job on that. So let's talk about this is f prime of x, which is same as f of x. Because derivative of antiderivative, you get the original one back. So remember that we can determine information for when f of x increases, decreases. We have to talk about whether the f of x increases, decreases, as well as relative extrema by looking at f prime. By looking at f prime. Using this table above, make a sign chart of f prime of x, determine the interval. So let's take a look at the sign chart. I'm going to make the sign chart here. This is the sign chart for f prime of x. So clearly this is a 0, 3, right? That's a 0, f prime. 6.5 is a 0. This is derivative is negative. Then, oh, there is a one more 0, 5. That's the positive, that's the negative, and that's the positive. So based on this sign chart of f prime of x, we can determine whether f is increasing, decreasing, relative maximum, minimum, everything back to the previous unit. You must write including context. You have to write what, where, why. So I'm going back on here based on this result. This is something non-negotiables. As soon as you see that f prime of x is the same as f of x, you must write these on the graph. You have to write this is the graph of f prime of x. We have done this in the previous unit. We are just looking at different perspective. This is the lowercase f. Based on the definition, derivative is the same as the, so this is the graph of uppercase f of x, derivative of uppercase f prime of x. You have to show this on the graph. You have to show this on the graph. And once we have this, we can justify all those answers, increasing, decreasing, relative max. You can clearly see that this is changing from positive to negative. So that means this is my relative maximum, negative to positive, positive to negative. All you can explain everything now based on this graph. So I'm going to show you what you should be writing and how. F of x, this is a what part, because we are talking about uppercase f. You are going to forget about the lowercase f. That's not we are going to see. That's just the part of the process. Uppercase f of x is increasing on 0 to 3. Increasing should be close parenthesis where it's positive. Reason is uppercase f prime of x equal to f of t is greater than 0. If you do not write this here, that's okay, as long as you establish the relationship that f prime of x is the same as f of t. You must establish this relationship somewhere on your paper. Then you can use any one of these. So where is relative maximum? Uppercase f of x has relative maximum at 3, f of 3. As this, you must have these critical values listed, f prime of 3 equal to 0. and f prime of x changes sign from positive to negative. Yes, we have more than relative. I mean, I did not write all those answers because I do not have a lot of space. I'm just pointing out how you are supposed to write it and taking you back on this like memory lane from the previous unit. I just wrote increasing and relative maximum. You can also write relative minimum. You can also write decreasing. This is the same as the previous unit. Same as the previous unit. The only difference is you are given the derivative graph. How do we establish the derivative graph is given to you based on the fundamental theorem of calculus that here if I take the derivative, I get the original function back. So this is the extra piece you are going to see. Well, we should be able to sketch the graph of the original one, just like the previous unit we did. So let's talk about the point of inflection. Remember, we can determine the information on concavity. F prime prime is greater than 0. So if we know that f prime of x is same as f of x, then prime prime is a f prime of x. Looking at the original curve, which is f of x, construct the sign chart for f prime of prime of x, determine whether f is concave up, concave down, and inflection points. So I'm going to take you up here. This is f prime of x. If I'm talking about concavity, I can see that f prime is increasing. That means second derivative positive, concave up, decreasing and decreasing. This is the between 2 and 4. Uppercase f of x is going to be concave down because f prime of x is decreasing. Here it is increasing between 4 and 6. It's going to be increasing because f prime of x, concave up because f prime of x is increasing and decreasing. Okay, so let's talk about POI. Where is a POI? Point of inflection is, this is a point of inflection where f prime of x is changing from increasing to decreasing, or it has a relative extrema. These are the only two point of inflection I have. 4 and 6, these are not point of inflection. No, you cannot consider them point of inflection. There is only 1 and 2, 4 and 6. So if we put all those informations together, this is going to be the graph of f of x. Where did I get all these points from is I just plot those points from the table. I plot those points from the table. The first table is 0 is a 0. And I just plot those points you can see from the first table, and I connected, and you can make connection that this is relative maximum 3, f of 3. This is relative minimum, another maximum, concavity. You can see concave up between 0 and 1, 4 and 6, concave up. So this is what you have to try to sketch the graph. I'm going to stop this video here. I highly recommend that you practice on the next page. At least try to fill in these blanks. And just explaining one more time, as soon as you see this, you are going to, I changed the name of the function so that it's much easier to see. As soon as you see this, you are going to write down on the paper that the derivative of g is a g prime of x. Derivative of f, here derivative, entire derivative, you get the original function back. So straight away write down that this is the graph of g prime of x. These are non-negotiables. You have to declare that you are given a graph of g prime of x based on the fundamental theorem of calculus, derivative of entire derivative, you get the original function back. So this is the graph of g prime of x. Once you write this, all is writing fill in the blanks. So why don't you fill in this table here, I mean all those values, and then we will discuss more in the class. And we have lots of practice problems all the way up to page number 40 is all the same. I'm going to stop this video here, and all these answers are posted in the classroom as well. So once you finish it, you can check your answer in the notes posted in the classroom. Thank you.